All right. Good morning, everyone. My name is Lex Fridman. I'm a research scientist here at MIT. I build autonomous vehicles and perception systems for these vehicles. And today I'd like to talk, first of all, it's great to be part of this amazing course in Intro to Deep Learning. It's a wonderful course covering pretty quickly but deeply some of the fundamental aspects of deep learning. This is awesome. So the topic that I'm perhaps most passionate about from the perspective of just being a researcher in artificial intelligence is deep reinforcement learning, which is a set of ideas and methods that teach agents to act in the real world. If you think about what machine learning is, it allows us to make sense of the world. But to truly have impact in the physical world, we need to also act in that world. So you bring the understanding that you extract from the world through the perception systems and actually decide to make actions. So you can think of intelligent systems as this kind of stack from the top to the bottom. From the environment at the top, the world that the agent operates in, and at the bottom is the effectors that actually make changes to the world by moving the robot, moving the agent in a way that changes the world, that acts in the world. And so from the environment, it goes to the sensors, sensing the raw sensory data, extracting the features, making sense of the features, understanding, forming representations, higher and higher order representations. From those representations, we gain knowledge that's useful, actionable. Finally, we reason, the thing that we hold so dear as human beings, the reasoning that builds and aggregates knowledge bases, and using that reasoning form short-term and long-term plans that finally turn into action and act in that world, changing it. So that's kind of the stack of artificial intelligence. And the question is, how much, in the same way as human beings, we learn most of this stack. When we're born, we know very little, and we take in 5 sensory sources of sensory data and make sense of the world, learn over time to act successfully in that world. How much, the question is, can we use deep learning methods to learn parts of the stack? The modules of the stack or the entire stack end to end? Let's go over them. Okay, so for robots that act in the world, autonomous vehicles, humanoid robots, drones, there are sensors, whether it's LiDAR, camera, microphone coming from the audio, networking for the communications, IMU getting the kinematics of the different vehicles. That's the raw data coming in. That's the eyes, ears, nose for robots. Then, once you have the sensory data, the task is to form representations on that data. You make sense of this raw pixels or raw pieces, samples from whatever the sensor is, and you start to try to piece it together into something that can be used to gain understanding. It's just numbers, and those numbers need to be converted into something that can be reasoned with. That's forming representations. And that's where machine learning, deep learning steps in and takes this raw sensory data with some pre-processing, some initial processing, and forming higher and higher order representations in that data that can be reasoned with about in the computer vision from edges to faces to entire entities, and finally the interpretation, the semantic interpretation of the scene. That's machine learning, playing with the representations. And the reasoning part, one of the exciting fundamental open challenges of machine learning is how does this greater and greater representation that can be formed through deep neural networks can then lead to reasoning, to building knowledge, not just a memorization task, which is taking supervised learning, memorizing patterns in the input data based on human annotations, but also and extracting those patterns, but also then taking that knowledge and building over time, as we humans do, building into something that can be called common sense, into knowledge bases. In a very trivial task, this means aggregating, fusing multiple types of extraction of knowledge. So from image recognition, you could think, if it looks like a duck in an image, it sounds like a duck with the audio, and then you could do activity recognition with the video. It swims like a duck, then it must be a duck. Just aggregating this trivial different sources of information. That's reasoning. Now, I think from the human perspective, from the very biased human perspective, one of the illustrative aspects of reasoning is theorem proving. is the moment of invention, of creative genius, of this breakthrough ideas as we humans come up with. I mean, really, these aren't new ideas. Whenever we come up with an interesting idea, they're not new. We're just collecting pieces of high-order representations of knowledge that we've gained over time, and then piecing them together to form something, some simple, beautiful distillation that is useful for the rest of the world. And one of my favorite sort of human stories and discoveries in pure theorem proving is Fermat's last theorem. It stood for 358 years. This is a trivial thing to explain. Most 8-year-olds can understand the definition of the conjecture that x to the n plus y to the n equals z to the n has no solution for n greater than 3, greater than or equal to 3. Okay, this has been unsolved. There's been hundreds of thousands of people try to solve it. And finally, Andrew Wiles from Oxford and Princeton had this final breakthrough moment in 1994. So he first proved it in 1993, and then it was shown that he failed. And then, so that's the human drama. And then, so he spent a year trying to find the solution, and there's this moment, this final breakthrough, 358 years after this first formed by Fermat as a conjecture. He said, it was so incredibly beautiful. It was so simple, so elegant. I couldn't understand how I'd missed it, and I just stared at it in disbelief for 20 minutes. This is him finally closing the loop, figuring out the final proof. I just stared at it in bit disbelief for 20 minutes. Then during the day, I walked around the department, and I keep coming back to my desk looking to see if it was still there. It was still there. I couldn't contain myself. I was so excited. It was the most important moment of my working life. Nothing I ever done, nothing I ever do again will mean as much. So this moment of breakthrough, how do we teach neural networks? How do we learn from data to achieve this level of breakthrough? That's the open question that I want you to sort of walk away from this part of the lecture thinking about. What is the future of agents that think? And Alexander will talk about the new future challenges next, but what can we use deep reinforcement learning to extend past memorization, past pattern recognition into something like reasoning and achieving this breakthrough moment? And at the very least, something brilliantly in 1995, after Andrew Wiles, Homer Simpson, and those that are fans of The Simpsons, actually proved him wrong. This is very interesting. So he found an example where it does hold true, the Fermat's theorem, to a certain number of digits after the period. Okay, and then finally, aggregating this knowledge into action. That's what deep reinforcement learning is about, extracting patterns from raw data, and then finally being able to estimate the state of the world around the agent in order to make successful action that completes a certain goal. And I will talk about the difference between agents that are learning from data and agents that are currently successfully being able to operate in this world. Example of the agents here from Boston Dynamics are ones that don't use any deep reinforcement learning, they don't learn from data. This is the open gap, the challenge that we have to solve. How do we use reinforcement learning methods, build robots, agents that act in the real world that learn from that world? Except for the perception task. So in this stack, you can think from the environment to the effectors, the promise, the beautiful power of deep learning is taking the raw sensory data and being able to, in an automated way, do feature learning to extract arbitrary high-order representations on that data. So make sense of the patterns in order to be able to learn in supervised learning, to learn the mapping of those patterns, arbitrarily high-order representations on those patterns, to extract actionable, useful knowledge. That's in the red box. So the promise of deep reinforcement learning, why it's so exciting for artificial intelligence community, why it captivates our imagination about the possibility towards achieving human-level general intelligence, is that you can take not just the end-to-end extraction of knowledge from raw sensory data, you can also do end-to-end from raw sensory data, be able to produce actions, to brute force learn from the raw data, the semantic context, the meaning of the world around you in order to successfully act in that world, end to end, just like we humans do. That's the promise. But we're in the very early stages of achieving that promise. So, any successful presentation must include cats. So, supervised learning and unsupervised learning and reinforcement learning sits in the middle. With supervised learning, most of the data has to come from the human. The insights about what is inside the data has to come from human annotations, and it's the task of the machine to learn how to generalize based on those human annotations over future examples it hasn't seen before. And on supervised learning, you have no human annotation. Reinforcement learning is somewhere in between, closer to unsupervised learning, where the annotations from humans, the information, the knowledge from humans is very sparse, extremely sparse. And so you have to use the temporal dynamics, the fact that in time, the continuity of our world through time, you have to use the sparse little rewards you have along the way to extend that over the entirety of the temporal domain to make some sense of the world, even though the rewards are really sparse. Those are two cats learning, Pavlov's cats, if you will, learning to ring the bell in order to get some food. That's the basic, for them, the reinforcement learning problem. So from supervised learning, you can think of those networks as memorizers. Reinforcement learning is, you can think of them crudely so as sort of brute force reasoning, trying to propagate rewards into extending how to make sense of the world in order to act in it. The pieces are simple. There's an environment, there's an agent, it takes actions in that agent, it senses the environment, so there's always a state that the agent senses, and then always, when taking an action, receives some kind of reward or punishment from that world. So we can model any kind of world in this way. You can model an arcade game, Breakout here, Atari Breakout. The agent has the capacity to act, move the paddle. It can influence the future state of the system by taking those actions, and it achieves a reward. There's a goal to this game. The goal is to maximize future reward. You can model the card pole balancing problem where you can control the pole angle, angular speed. You can control the card position, the horizontal velocity. The actions of that is the pushing the cart, applying the force to the cart, and the task is to balance the pole. Okay, and the reward is 1 at each time step the pole is still upright. That's the goal. So that's a simple formulation of state, action, reward. You can play a game of Doom with a state being the raw pixels of the game, and the actions are moving the player around, shooting, and the reward positive when eliminating an opponent, and negative when the agent is eliminated. It's just a game. Industrial robotics, any kind of humanoid robotics, when you have to control multiple degrees of freedom, control a robotic arm, control a robot. The state is the raw pixels of the real world coming into the sensors of the robot. The actions are the possible actions the robot can take, so manipulating each of its sensors, actuators. And then the reward is positive when placing a device successfully, negative otherwise. So the task is to pick something up, put it back down. Okay, so, and I'd like to continue this trajectory further and further complex systems to think the biggest challenge for reinforcement learning is formulating the world that we need to solve, the set of goals, in such a way that we can apply these deep reinforcement or reinforcement learning methods. So give you an intuition about us humans, it's exceptionally difficult to formulate the goals of life. Is it survival, homeostasis, happiness, who knows? Citations, depending on who you are. So the state, sight, hearing, taste, smell, touch, that's the raw sensory data. Actions are think, move, what else? I don't know. And then the reward is just, it's open. All these questions are open. So if we want to actually start to create more and more intelligent systems, it's hard to formulate what the goals are, what the state space is, what the action space is. If you take away anything sort of in a practical sense from today, from the deep reinforcement learning part here, a few slides, is that there's a fun part and a hard part to all of this work. So the fun part, what this course is about, I hope, is to inspire people about the amazing, interesting, fundamental algorithms of deep learning. That's the fun part. The hard part is the collecting and annotating a huge amount of representative data. In deep learning, in forming high-order representations, data does the hard work. So data is everything. Once you have good algorithms, data is everything. In deep reinforcement learning, the fun part, again, is these algorithms. We'll talk about them today. We'll overview them. But the hard part is defining the world, the action space, and the reward space. Just defining, formalizing the problem is actually exceptionally difficult when you start to try to create an agent that operates in the real world and actually operates with other human beings or actually significantly helps in the world. So this isn't playing an arcade game where everything is clean or playing chess go. It's when you're operating in the real world, everything is messy. How do you formalize that? That's the hard part. And then the hardest part is getting a lot of meaningful data that represents, that fits into that formalization that you formed. Okay, in the Markov decision process that's underlying the thinking of reinforcement learning, there's a state, you take an action, receive a reward, and then observe the next state. So it's always state, action, reward, state. That's the sample of data you get as an agent acting in the world. State, action, reward, state. There's a policy where an agent tries to form a policy how to act in the world, so that in whatever state it's in, it has a preference to act in a certain way in order to optimize the reward. There's a value function that can estimate how good a certain action is in a certain state, and there is sometimes a model that the agent forms about the world. A quick example. You can have a robot in a room at the bottom left, moving about this room. It's a 3x4 grid. It tries to get to the top right because it's a +1, but because it's a stochastic system, when it chooses to go up, it sometimes goes left and right 10% of the time. So in this world, it has to try to come up with a policy. So what's a policy? Is this a solution? So starting at the bottom, arrows show the actions whenever you're in that state that you would like to take. So this is a pretty good solution to get to the +1 in a deterministic world. In a stochastic world, when you go up, you don't always go up. It's not a optimal policy because you have to have, an optimal policy has to have an answer for every single state you might be in. So the optimal policy would look something like this. Now, that's for when the cost, the reward is negative 0.01 for taking a step. Now, every time we take a step, it's really painful. It's you get a -2 reward, and so there's the optimal policy changes. There's no matter the stochasticity of the system, the randomness, you want to get to the end as fast as possible. Even if you go through negative states, you just want to get to the +1 as quickly as possible. And then, so the reward structure changes the optimum policy. If we make the reward -0.1, then there's some more incentive to explore. And as we increase that reward or decrease the punishment of taking a step, more and more exploration is encouraged until we get to the kind of what I think of as college, which is you encourage exploration by having a positive reward to moving around, and so you never want to get to the end. You just kind of walk around the world without ever reaching the end. Okay, so the main goal is to really optimize reward in this world. And because the reward is collected over time, you want to have some estimate of future reward. And because you don't have a perfect estimate of the future, you have to discount that reward over time. So the goal is to maximize the discounted reward over time. And then Q-learning is an approach that I'd like to focus in on today. There's a state action value, Q. It's a Q function that takes in a state and action and tells you the value of that state. It's off policy because we can learn this function without without keeping an optimal policy, an estimate of an optimal policy with us. And what it turns out with the equation at the bottom, with the Bellman equation, you can estimate you can update your estimate of the Q function in such a way that over time it converges to an optimal policy. And the update is simple. You have an estimate. You start knowing nothing. There's this estimate of an old state, QSAT, and then you take an action, you collect a reward, and you update your estimate based on the reward you received and the difference between what you expected and what you actually received. And that's the update. So you walk around this world exploring until you form better and better understanding of what is a good action to take in each individual state. And there's always, as in life and in reinforcement learning and any agents that act, there's a learning stage where you have to explore. Exploring pays off when you know very little. The more and more you learn, the less and less valuable it is to explore, and you want to exploit, you want to take greedy actions. And that's always the balance. You start exploring at first, but eventually you want to make some money, whatever the metric of success is, and then you want to focus on a policy that you've converged towards that is pretty good, near optimal policy in order to act in a greedy way. As you move around with this Bellman equation, move around the world, taking different states, different actions, you can update you can think of it as a Q table, and you can update the quality of taking a certain action in a certain state. So that's a picture of a table there in the world with 4 states and 4 actions, and you can move around using the Bellman equation, updating the value of being in that state. The problem is when this Q table grows exponentially, in order to represent raw sensory data like we humans have when taking in vision, or if you take in the raw pixels of an arcade game, that's the number of pixels that are there is larger than can be stored in memory, is larger than can be explored through simulation. It's exceptionally large. And if we know anything about exceptionally large high-dimensional spaces and learning anything about them, that's what deep neural networks are good at. Forming the approximators, forming some kind of representation on an exceptionally high-dimensional complex space. So that's the hope for deep reinforcement learning, is you take these reinforcement learning ideas where an agent acts in the world and learns something about that world, and we use a neural network as the approximator, as the thing that the agent uses in order to approximate the quality, either approximate the policy or approximate the quality of taking a certain action in a certain state, and therefore making sense of this raw information. Forming higher and higher order representations of the raw sensory information in order to then, as an output, take an action. So the neural network is injected as a function approximator into the Q. It's the Q function is approximated with a neural network. That's DQN. That's deep Q learning. So injecting into the Q learning framework a neural network. That's what's been the success for DeepMind with playing the Atari games. Having this neural network takes in the raw pixels of the Atari game and produces actions or values of each individual actions, and then in a greedy way picking the best action. And the learning, the loss function for these networks is twofold. So you have a Q function, an estimate of taking a certain action in a certain state. You take that action, and then you observe how the actual reward received is different. So you have a target, you have a prediction, and the loss is the squared error between those two. And DQN uses the same network, the traditional DQN, the first, DQN uses one network to estimate both Qs in that loss function. A double DQN, DQN uses a separate network for each one of those. A few tricks, they're key, experience replay. So tricks in reinforcement learning, because the fact that it works is incredible, and as a fundamental sort of philosophical idea, knowing so little and being able to make sense from such a high-dimensional space is amazing. But actually, these ideas have been around for quite a long time, and a few key tricks is what made them really work. So in the first, I think the 2 things for DQN is experience replay, is instead of letting the agent learn as it acts in the world, agent is acting in the world and collecting experiences that can be replayed through the learning. So the learning process jumps around through memory, through the experiences, and instead, so it doesn't learn on the local evolution of a particular simulation, and instead learn of the entirety of its experiences. Then the fixed target network, as I mentioned with double DQN, the fact that the loss function it includes, if you notice, sort of two forward passes through the neural network. And so because when you know very little in the beginning, it's a very unstable system, and bias can have a significant negative effect. So there's some benefit for the target the forward pass the neural network takes for the target function to be fixed and only be updated, the neural network there to be only updated every 1,100 steps. And there's a few other tricks. The slides are available online. There's a few interesting bits throughout these slides. Please check them out. There's a lot of interesting results here on this slide and showing the benefit that you get from these tricks. So replay, experience replay, and fixed target network are the biggest. That's the magic. That's the thing that made it work for the Atari games. And the result was DeepMind achieving super above human level performance on these Atari games. Now, what's been very successfully used now with AlphaGo and the other more complex systems is policy gradients, which is a slight variation on this idea of applying neural networks in this deep reinforcement learning space. So DQN is Q-learning. It's using neural network in the Q-learning framework. It's off policy. So it's approximating Q and infer the optimal policy. Policy gradients, PG, is on policy. It's directly optimizing the policy space. So the neural network is estimating the probability of taking a certain action. And the learning, and there's a great, if you want the details of this from Andre Karpathy, it's a great post explaining in an illustrative way deep reinforcement learning by looking at Pong, playing Pong. So the training process there is you look at the evolution of the different games and then reinforce, also known as actor-critic. You take the policy gradient that increases the probability of good action and decrease the probability of bad action. So the policy network is the actor. So the neural network is the thing that takes in the raw pixels, usually a sequence of frames, and outputs a probability of taking a certain action. So you want to reward actions that have eventually led to a winning a high reward, and you want to you want to decrease, have negative gradient for actions that that led to a negative reward. So the reward there is the critic. The policy network is the actor. The pros and cons of DQN, of policy gradients versus DQN. Most folks now, the success comes from policy gradients, actor-critic methods, different variations of it. The pros are it's able to deal with more complex Q function. It's faster convergence in most cases. Given you have enough data. That's the big con, is it needs a lot of data. It needs a lot of ability to simulate huge amounts of evolutions of the system. And because the model probabilities, the policy gradients model the probabilities of action, they're able to learn stochastic policies, and DQN cannot. And that's where the game of Go has received a lot of success with the application of the policy gradients, where at first AlphaGo in 2016 beat the top humans in the world at the game of Go by training on expert games. So in a supervised way, starting from training on those human expert positions. And AlphaGo 0 in 2017, achieving a monumental feat in artificial intelligence, one of the greatest, in my opinion, in the last decade, of training on no human expert playing against itself, being able to beat the initial AlphaGo and beat the best human players in the world. This is an incredible achievement for reinforcement learning that captivated our imagination of what's possible with these approaches. But the actual approach, and you can look through the slides, there's a few interesting tidbits in there, but it's using the same kind of methodology that a lot of game engines have been using, and certainly Go players for the Monte Carlo tree search. So you have this incredibly huge search space, and you have to figure out like which parts of it do I search in order to find the good positions, the good actions. And so there, neural networks are used to do the estimation of what are the good actions, what are the good positions. Again, the slides have the fun details. For those of you who are gambling addicts, this is importantly so, the stochastic element of poker, at least heads-up poker, so one-on-one, has been, for the first time ever, this same exact approach have been used in DeepStack and other agents to beat the top professional poker players in the world in 2017. The open challenge for the community, for maybe people in this room in 2018, is to apply these methods to win in a much more complex environment of tournament play when there's multiple players. So heads-up poker is a much easier problem. The human element is much more formalizable and clear there. When there's multiple players, it's exceptionally difficult and fascinating problem. That's perhaps more representative of agents that have to act in the real world. So now the downer part. A lot of the successful agents that we work with here at MIT and build, the robots that act in the real world, are using almost no deep reinforcement learning. So deep reinforcement learning is successfully applied in context of simulation, in context of game playing, but in successfully controlling humanoid robotics or humanoid robots or autonomous vehicles, for example. The deep learning methods are used primarily for the perception task. They're exceptionally good at making sense of the environment and extracting useful knowledge from it, but in terms of forming actions, that's usually done through optimization-based methods. Finally, a quick comment on the unexpected local pockets. That's at the core of why these methods are not used in the real world. Here is a game of Coast Runners where a boat is tasked with receiving a lot of points. Traditionally, the game is played by racing other boats and trying to get to the finish as quickly as possible. And this boat figures out that it doesn't need to do that in a brilliant breakthrough idea. It can just collect the regenerating green squares. That's an unintended consequence that you can extend to other systems, perhaps, including you can imagine how the cat system over time at the bottom right can evolve into something undesirable. And further on in these reinforcement learning agents, when they act in the real world, the human life is often, the human factor are often injected into the system. And so oftentimes in the reward function, the objective loss function, you start injecting concepts of risk and even human life. So what does it look like in terms of AI safety when an agent has to make decisions based on a loss function that includes an estimate or risk of killing another human being? This is a very important thing to think about machines that learn from data. And finally, to play around, there's a lot of ways to explore and learn about deep reinforcement learning, and we have at the URL below there a deep traffic simulation game. It's a competition where you get to build a car that speeds, that tries to achieve as close to 80 miles per hour as possible, and I encourage you to participate and try to win, get to the leaderboard. Not enough MIT folks are at the top 10. So with that, thank you very much. Thank you for having me.